We have David Meyer with Brocade. This is a complex talk. Bad pun. Get your thinking caps on. Be ready for this. Good time to pay attention. If you're reading your email, you're going to miss something here. Dave, thanks for being here. So let's see. What do I have? Okay. Wow. This is pretty cool. I kind of came on the scene around NANOG 3. It was a different scene altogether. I think there were like 25 people there. It was in Boulder. So this talk is about complex systems. And, I'm going to give you a little bit of a motivation about, why, if I can figure out how to use the clicker, about why to even think about this. I'm really not going to talk about this picture, but I love this picture on the title slide. It kind of shows that as engineers, we build things, but we use principles that are found everywhere around in nature and in other kinds of engineering disciplines and things like that. And so, the idea is that we can probably learn some things. So I'll tell you what I've learned. Let's see. Okay, so agenda is something like this. As always, I have too many slides, too many words. I want to tell you guys all kinds of things, so I have to I'm going to go kind of fast over some of it, but I wanted to put it in the deck so you can have it if you want it. I put some stuff about motivation and goals for this talk, and then what is complexity, why is it hidden, why do we care, what is robustness, fragility, what does it have to do with networking, and are there some principles that we can build engineering discipline or rules from, like you have maybe in mechanical engineering or something like that. And then I'll give you a few conclusions, and I don't know if we'll have time for Q&A, but if so, if not, by the way, drop me an email or pull me over anytime. Glad to talk about this stuff. So this is the Danger Will Robinson slide. This talk is going to be controversial and provocative in some sense and kind of sciencey, so this is kind of like my standard disclaimer. It's a little bit sciencey. I don't think that's a word, by the way. All right, so how to motivate all of this. How to get involved in this. It's really this, right? I mean, it was really SprintLink. I was working at Sprint around 2000. And what happened was, this is the SprintLink domestic DWDM network around that time. And what happened was, like always happens, is the SprintLink crew was out in Reston, and we were happily doing our thing, sort of subversively, out in Reston, and we got reorged to report up through Kansas City, right? And this happened somewhere around 2000, something around 2000, right? And all the SprintLink folks were now reporting up through Kansas City, but that was famously the home of pin drop, ATM, frame relay, and TDM, among other things. So you could see there was a little bit of a culture clash there. So we had been talking about, so this is like Peter, Ted, all of these folks, right, and Sean even. We'd been talking about how IP was the simpler way to do networking and how it scaled better and all this stuff. And so I get to the new Kansas City thing, and I finally get out to Kansas City, which was an interesting experience in and of itself. But so somebody asked me, why is the IP network so much simpler, and why, if it is, why is the OpEx CapEx profile so much higher than these other platforms that were there, like ATM and frame relay? And I just couldn't answer that question. I was just clueless, completely, no clue. So, there were all kinds of talks about, FCAPS is built into this, or, there's NMS, or all of this kind of stuff, but nothing was really quantitative at all about how to analyze this. There was no way, I had no way of analyzing it, right? So it kind of set off to figure out how I might answer it. First by surveying what was the complexity literature, which, itself was not too, there wasn't a lot. And I got myself all confused. I didn't even know what complexity was for a while, or still, maybe. And I was sure there was a way to, a quantitative way to compare it, like circuit switch and packet switch networks. I was sure of that, except for there wasn't. So what happened was, I did a lot of work with a lot of people in the internet community, just trying to understand how you might get at this question, right? And one result was RFC 3439, which started its life as sort of my kind of attempt at trying to categorize what was going on inside SprintLink and inside the Sprint ATM and frame relay networks, and kind of expanded it to this. And this was from, I think NANOG 26, we had a panel where we talked about this. And this is one of my slides, and RFC 3439 was kind of organized around this idea that Mike Odell had, which was stated here, which is, complexity is the primary mechanism that impedes efficient scaling and blah, blah, blah. And that was my slide, by the way. I was using Magic Point at the time, so all I can do is screen capture the ones I have now. So, but this was the idea, right? And so we kind of built a story around this, and that's what's in RFC 3439. There was kind of one problem. It was all cool, but and there was some compelling stuff in 3439 that's still relevant, but it doesn't really talk about what complexity is. In particular, it didn't tell us what it was or where it comes from or what, anything really. So, we thought it had to do with something called coupling and amplification. You can see these things in the network all the time. Coupling is a thing where one or more processes get stuck together somehow. So a canonical example of that was what slow start synchronization, right? Before backoff slow start was randomized, if there was a bottleneck in the network somewhere, all of the TCP sessions going through there would drop a packet, and then they'd all back off, and so they were synchronized. Randomness solved that. Amplification we still see every day, right? So DOS attacks, multiplication of updates in the peering mesh of the internet, things like that. We thought that's what it was about. But the problem was there was no explanatory power or predictive power in the whole thing. We couldn't use it for anything. We couldn't build engineering rules. So, the classic error was it confused sort of the symptoms with root cause. So we had to go and find something a little bit deeper. There was no theoretical, mathematical, nothing that we could use to lean on. So it was kind of here that I kind of started, kind of looking around at what kind of machinery was available to kind of think about this. Because the underlying, by the way, the underlying thing here is that you can use engineering heuristics. That's what we do right now. We have great sense about how to build a network, and we've built it, and it gets bigger all the time. But there's an idea that might have a limit, and you can see this in things like building construction and basically all of technology. At some point you have to kind of have a sort of a way of analyzing things a little bit more quantitatively. Whether or not we're there yet, that's left to be seen. But anyway, so I started working with people in the control theory and systems biology and engineering communities, trying to get at some of these questions, like what machinery is out there. So that's how this all started, and that's really where we are at in the sort of evolution of all of this stuff. The understanding of systems like the internet or biological systems is pretty primitive. But we also wanted to understand the practical implications of all of this for engineering, for us. Because if we don't have that, it's kind of not that useful. So goals. I want to characterize for you a little bit what I've learned to be the essential features of complexity and how it fits with what we're doing. What are the trade-offs? Trade-offs are something that the theory guys use. They mean laws, like mathematical laws, but we call it trade-offs, and I'll show you what that means. And there's a relationship between trade-offs, complexity trade-offs, and layering. Layering's a big thing in networking. Maybe they can be used to build a useful theoretical framework. What useful means is that you can derive engineering rules from it. You can build bigger, more efficient, more scalable networks. That's what useful means. And then begin to bridge the engineering and theory networking community. It's a big theory networking community, but they don't have access to all of you folks. So they do need it too, because they need to know what's real. I mean, if you don't kind of rein those guys in, who knows what they'll do. So they need to know what's real, but we also need the kind of tools we can get from them. So it's kind of a bridge building thing there. Okay, so said another way. This is too many words. But the goal of this is just open up the thinking about what networking really is and what tools we can use and how we can bring this all together and kind of understand our network better and make it scale better, build it better, all of the things we want to do. So with that, that's kind of the motivation. So SprintLink, blame SprintLink. Hey, I saw some SprintLink alumni out here too. Okay, so what is complexity and why is it hidden? So this is the robustness, complexity, fragility piece of all of this. So basically, what is it? So frequently when you talk to people about complexity, you go, oh, that's complex because it has a lot of parts. But that's not really what it is. It's really about structure. And that structure that arises in these systems, and structure that arises in systems like the internet. like the pairing mesh of the internet, for example. And the reason that it exists is to create robustness to environmental and component uncertainty. So what do? If you want to have, if you want to protect against, say, one or n circuits going down, you put another router and some other circuits, and you kind of build structure redundancy that's about creating a robustness to environmental or component failure. So why is it hidden? There's a reason why it's hidden, by the way. That's a fundamental piece of it, and I'll show you this in a second. But if you think about it, all of these control systems that we have in complex systems that we encounter every day are kind of hidden. Like anti-lock brakes in your car, you don't ever notice them until they lock up. TCP, you don't really ever notice it until packets start getting lost. Linux kernel has this, Power Grid has this, cloud stacks, all of this stuff. And they're basically have this property that you never notice that they're there until they fail, and then they often fail catastrophically. Power Grid, things like that. So why is it hidden? It's a fundamental property in these systems. It's sort of like, it derives from these principles of complex systems that involve layering. So one way to think about it is if you're building software, you really want to have APIs that don't expose the implementation of what's underneath it, but expose some kind of a semantics about what the operation is, and that's kind of hidden. And it's kind of the same thing in a way. So it's also required to make robustness and evolvability compatible. By the way, evolvability is kind of a new requirement for us in the networking world. So when you go and talk to a cloud provider, they're always talking to you about, how can I be more agile? How can I evolve my services? So evolvability is kind of a new requirement, but it fits in with this stuff directly. So it's evil, right? Complexity is bad. I mean, that was really the story at Sprint. This stuff, ATM, this stuff is too complicated. IP is simpler. Isn't complexity just evil? And we'll get to a better definition of what robustness is in a second. But I don't know how many times people have told me, that's too complicated. That's evil for complexity. But when you look at it, what it really is it's not inherently evil. What it is that a system needs complexity to achieve robustness. That's really what it's there for. The problem is that we have a tendency to go beyond the point where you're getting additional robustness out of it, and then things start going poorly, right? So in some configuration of a system, the amount of complexity, the amount of robustness you can get is bounded, but the amount of complexity you can put into it isn't. So if you get over into the fragile side of that, that's where you need to start looking for a new job, because basically you've gone over the bad side of this. And so this is kind of one way to look at the trade-off between complexity and robustness. I'll show you another way in a second that is a little bit more quantitative. But the thing to remember here is that you need complexity to get robustness. And if you don't have that, then systems can be not quite as sophisticated. So it's not an inherently evil thing. It's just that you don't want too much of it, where it doesn't buy you anything. So what's robustness then? Because I'm saying there's a trade-off between complexity and robustness. Well, it's a generalized feature of these systems. And what do I mean by generalized? Well, if you look at this, scalability is a kind of robustness. It's a robustness that changes in size and the complexity of the system as a whole. Reliability is a kind of robustness when it's robust to component failures. That's what reliability is. Efficiency is robustness to resource scarcity. Modularity is robustness to component rearrangement. So we want modular, efficient, reliable, scalable networks, right? So there's a lot of these. So it's a very general idea. It captures a lot of the features that we're seeking from the network, and so it's a decent thing to kind of try to think about in terms of the trade-off that you're making between how robust you can make a network, what dimension you're looking at, and how it interacts with the complexity that you're putting into it. So here's a bit more formal thing. Robustness is basically the preservation of some property in the presence of uncertainty in the components or in the environment. So it's basically the fact that you have some kind of steady state and you can maintain that. Obviously, that's a core internet design principle. And in systems biology, they just say, biological systems are designed. People always kind of core dump on the design thing. Don't spend too much time with that. But biological systems are designed so they're important functions, they work, and they're insensitive to whatever the variations, naturally occurring variations are in their, the parameters of whatever they're doing. And of course, if you drop a bomb on a bacteria, it's not robust to that. So, the exact adaptation in bacterial chemotaxis is a cool thing. The bacteria can swim up a gradient of sugar if they want, and it's got all this interesting feedback control that actually we could learn something from, but that's a whole nother topic. Fragility is kind of the opposite of robustness, and there's another way to think about it. It's kind of like when things are sensitive to second order effects. I'll show you an example of that, but it's basically the opposite. And then this is the important thing. This is the important piece of this whole complexity robustness stuff, is that a system can have a property, something that it's robust to one set of perturbations, but it's fragile to a different property or set. So the system's called robust yet fragile. And of course, if you drop a bomb on it, it's above some kind of threshold, and then you call it K fragile, above some K. But basically, the thing to notice here is that a system can be robust yet fragile at the same time. And there's actually a conservation law at work here that's kind of interesting that we don't build into our thinking, and I'll show you in a second what that is. So what's an RYF trade-off? So robust yet fragile, RYF, right? And that's common terminology in the communities that look at this stuff. So you can, a possible trade-off, RYF trade-off would be something like if you want high efficiency, you want to be robust to minimal resource utilization, it might be unreliable or fragile, right? Because you optimize, and when you optimize things, they become fragile or they're hard to change. So here's an example of how you get robust yet fragile. This is the one I always use. It's basically, I remember when we first built networking at U of O, we did the obvious thing. We put an interface into every building. Everybody had a subnet at 24 or whatever it was. And what we found was, okay, that's cool, but it's fragile, not robust, to failure of that one interface. So we wanted to make it more robust. So the obvious thing to do was put another router interface in it and run VRRP or HSRP at the time between them, right? And so that caused robustness to failure of one of the interfaces, but it caused new kinds of fragility. For example, the keep alive for who owned the MAC address for the default address always was screwing up because there was code there that wasn't there before, and things like that. So what you did was you created robustness to one thing, but in the process of doing that, you created fragility. And basically this spirals. So you need complexity to get robustness, but complexity has this RYF property, so there's fragility. So when you build something, you create robustness, that creates fragility. You add more complexity to overcome that fragility, and you get in a spiral. And we see that all the time. And HA, ISSU, all of that stuff has these properties. Seems like kind of a contradiction. It took me a while to get my head around it. Robust yet fragile. So as I said, a system can have a property that's robust to something, yet it can be fragile to a different property or different kind of thing. That's really the core thing here. And this is like a core property of these dynamic systems. There's another interesting thing, and I just threw this in here, but basically if you kind of compute some kind of harm function, like how bad does this hurt, it's robust if it's concave, like I guess it's on your right there, and if you do that graph and it's convex, you'll have a fragile thing. So it's interesting that turns out to be that way, but more interesting is really this. So there's recent results that say that this RYF trade-off, and I was saying, you have to, if you create robustness, you're going to create fragility somewhere else. There's recent results that suggest that this is actually a hard trade-off. This is something you cannot get around, and it's kind of profound. I mean, what it's saying is, if you create robustness in your network, you'll create fragility somewhere else. But the question is where? And we don't have the technology to tell you that, But in network engineering and most other engineering disciplines for that matter really don't account for this or even think about it. What we do is we get involved in this spiral, right? You build something, it's more robust to something, but then there's some condition that triggers some fragility. Okay, so fix that, and now we're in that spiral, and that's also characteristic. But this is kind of one of the things where if you actually had some way of thinking about this and actually computing, if I have this and I do this, will I get fragility here or there? That would be very, very useful and really, really be a great breakthrough, but we don't have that. So maybe interestingly, fragility and scaling are kind of related. And that seems kind of counterintuitive maybe too, is that basically, if you want to make a little bit more of a formal description of what it means to be fragile, so if you just have you have a harm function, negatively valued harm function, that's what this H thing is, and you have some perturbation and some stress thing, right? So basically what this says is that if you're fragile, the stress that you get from the cumulative effects of some event are non-linearly worse than one of the big ones, right? So here's an example. So a big event hurts non-linearly more than the sum of small ones. And here's the example. And this is kind of an interesting example. So basically, if you had a coffee cup, I don't have one, but if you were kind of like going like this with it, so it's like what, 3 inches, you do it 100 times, and the coffee cup survives. It's no problem. But if you dropped it once from like say 20 feet, which was the sum of all of those things, it would be destroyed. So it's non-linearly fragile to the big event versus the sum of the small ones. And we see that all the time. And by the way, it's interesting because nature actually requires this of us, right? Because if you consider how much do you walk around, you lift your feet up and, maybe it's 5 inches or, 3 inches every time, and you've walked miles and miles and miles. So jumping off something a mile high versus walking a mile, damage is non-linearly related. So how's that related to scaling? So how many people have said something like, oh, that scales like n squared? Networking people, we say that all the time, right? Because they're pairwise, right? And so when things start being pairwise, it scales like n squared. But there's another way to interpret that. And one way you can interpret it is you can say that the damage caused by these events are non-linearly related. In this case, I said n squared, but it's like the second derivative, right? So that would be 2. So the constant acceleration of damage for weird enough n's, something outside like 3 sigma or something. Doesn't happen very much, but we've gotten it a lot, ARP storms, congestion collapse on the early internet. Who remembers AS7007? That wasn't so good. That was non-linearly damaging. So there's all kinds of examples of this. So it's all about these trade-offs. And so you try to draw a graph of it, right? What's the trade-off? So this thing that's the theorem, it's, all it is saying that the stuff down in sort of by the origin where it says fragile and simple on this one, you can't get there. And so if you build a theorem that looks like that, right, like that, you'll get that nice curve that shows you a trade-off that looks like that. It's not really quantitative in any way. It's just showing you, hey, you can't get to fragile, you can't get to robust and simple very easily, right? So because you need complexity to get robustness, you can't get there. So, and then the line is kind of the trade-off frontier. You kind of just move back and forth along there. And I'll show you some examples of that, how that really works in the world. So biology and technology try to be robust and simple. That's pretty tough. You can't really get there. Physics, well, a lot of us think it's kind of hard and fragile. And then, if you get over here, you got to find a new job. Yeah, basically. So, and how many people know people who have designed stuff that lives over there? I certainly do. It happens. And those people actually did have to find a new job. So this RYF stuff, though, this is, so this is sort of a way of drawing the RYF trade-off, right? But if you look in nature and in engineering and the stuff we do, this stuff is everywhere. So if you look at the way, efficient and flexible metabolism like we have works, it's very robust, but exactly the same mechanisms are hijacked to create, the fragile piece of it. Complex development, microbial ecosystems, immune system, how many people have autoimmune disease, and it uses the exact same mechanism. Regeneration and renewal, you cut your finger, it uses the same thing as regeneration, and part of what developmental biology does. What's the fragile piece of that? Cancer, same mechanism. Complex societies, in complex societies, great stuff happens, but we get wars, like epidemics. In advanced technology, well, we know what happens, what can happen. So this is really everywhere. So it turns out that these evolved mechanisms, they call them evolved, for some means that they're at least somehow advanced. The mechanisms that cause this robustness, they actually allow for, and in fact, they actually facilitate these novel and severe fragilities elsewhere. And that's just another way of saying they're RYF complex. They have this RYF complexity thing. And they often involve hijacking, predation, and exploitation of the same mechanism that creates the robustness. So obviously we've seen this in the internet, DDoS attacks, right? If the openness of the IP sort of interface wasn't there, some of these attacks wouldn't be available. And as I said earlier, these are kind of hard trade-offs. In some ways, you can't get around this stuff. But what can we do with that from an engineering perspective? Right now, nothing. So early days. Talk to your neighborhood theorist. Get some tools. So if you want to summarize this RYF stuff, it is kind of the challenge that we're facing in trying to understand complex networks, both technological and biological, and any other kind, if there are other kinds. That is the challenge that we're facing. And it turns out that managing this and understanding this is really an essential challenge. And it pops up in technology, society, politics, ecosystems, everywhere. So where does that come from? Okay, so there are some universal architectural principles I want to tell you about that will kind of give you an idea of where this comes from. By the way, this is sort of a high-level view of this, and I'm trying to keep all the math out of it. The theory guys just love this math stuff. And it turns out that it's the natural language for this, but it makes it a lot harder to understand. So I try to avoid it when possible, at least when trying to understand things. So, basically what all this means is that there's architectural principles, and we have these in our network everywhere. And they're layering, bow ties, hourglasses, constraints, and I'll talk about this in a second. And then managing, remember I told you this RYF stuff causes this spiraling complexity, right? And we've seen this. I mean, I need 5 nines, no, I need 6 nines, I need 7 nines, and to do that, you have this, significant complexity. And the other thing is, there's this issue of predicting what is likely or typical, and that's always useful, but it's not the hard part. What's hard is understanding what's going to cause a catastrophic failure, and we don't have any tools for that right now. And Talab, who's one of my colleagues in all of this stuff, the guy who wrote the Black Swan, he calls it this fat-tailed, and I don't know if you can see this picture, but basically the way to think about it is if you get a little bit away from the mean, instead of letting the tail of the distribution go down, it stays this big. So it stays big like this. So that means that rare events cause catastrophic, consequences. So that's what the Black Swan really is. That is actually the same thing, strangely enough. And also, we create a lot of robust features, and it's easier to create them than it is to prevent fragility. In fact, we don't even know how to predict where it will come from. I mean, we have engineering heuristics that tell us, but we can't do it in the quantitative work. And as I mentioned, there are these very poorly understood conservation laws that are at work here. This stuff is somehow conserved. So the bottom line is that somehow we have to find out how to understand RYF behavior and the associated trade-offs. And that means understanding network architecture and all this hidden nature of this. And so that's kind of what's underlying all this. Now, what is our architecture? What is the architecture of our network, and what trade-offs are being made? Well, how many people have seen this? Internet Hourglass? This was, I think, originally drawn by Steve Deering. This is one of the many ones, and I'll talk more about this particular one. But this was sort of like, that's what the internet was. That was the protocol stack of the internet at some point in history. People argue about what it is now, but I'll just put it this way. It's more like this, right? I mean, the OpenStack, open this, open that, NFV, all of these kind of things that are impinging on data center operations or DCI operations, along with the way it affects sort of the transport network. So all of this stuff is around, but nobody's really going, well, how do we hook all these things together, and what does it mean? We just kind of do it with engineering heuristics, and we've gotten a long way with that. So we gotta give ourselves a pat on the back for that. But there's also this. I had a picture of Raz in here, but I thought this might be more descriptive. Basically, open source is like DNA floating around in a bacterial ecosystem, and it's mutating all the time. And what does that all mean? I happen to be involved in an open source project right now, and I kind of think about that a lot because I see a lot of good mutations and bad mutations, if you will. So what are the fundamental trade-offs that we're making, and is there a more general way to think about it? I kind of thought that. So I tried to do this. Okay, I couldn't find a good picture of what it might mean to write machine code, but the idea is, like, if you write assembly language code, what you think you're doing is, the reason you do it is because you do it for performance, right? And on the right, there's a chunk of Python, so maybe it's interpreted. So the idea is that there's some speed versus flexibility trade-off that we're making here. And, what about this? This is the, okay, now I'm NFV or something like that. So bare metal versus virtual machines versus maybe containers. What's the trade-off? It's kind of speed versus flexibility again, right? So there's a bunch of these out there, binary versus machine code, or versus something interpreted, VM, bare metal, containers. How many people remember fast and slow path? Features got in hardware if they had to be fast and somebody could pay for it. Otherwise they were slow, but they were more flexible and slow. So hardware versus software is kind of a more general way of it. Convergence time versus state in routing protocols, trade-offs. So are there essential features of these, and can we use them somehow for engineering? I mean, that's really what we're trying to get at here. What are the fundamental trade-off spaces? Are there laws? So the theory guys like laws. And can we drive some engineering benefit from this, right? Because again, it's really difficult to, to see where the theory is going, but you can kind of nudge it in a way that's useful if you can give these folks some input. And then how do they relate to all this RYF stuff? So it turns out that trade-offs in the RYF space in complexity are really fundamental. And this will probably take you back to your undergraduate theory of computer science course, so I won't stay too long on this, but remember this, we had this thing, right? So there's some frontier there where you're making a trade-off between robustness and complexity. But basically, that's a picture of Alan Turing. Alan Turing kind of invented the split between software and hardware. He invented AI. He was a world-class runner too, by the way. But basically, he came up with these theoretical constructs that were like laws. They're impossible to get beyond. And then above that was where people did architecture. So, for example, you can't have a fast and general computation element. Basically, if you want to go fast, you have to have inflexible special purpose hardware, basically, is what it comes down to. And if you go slow, you can do it in software. So how does that look? Well, if you drill down on the computational complexity piece of it, if you go to where you're super general or beyond that, undecidable is more than general, it's not computable, that's really, really slow. But if you go to the right on the x-axis and you get to these things that are in what are called polynomial time, which is really restricted problems, you can do those pretty fast. So it's kind of a trade-off between whether or not you can run fast or you're general. That's the basic trade-off there. Now I'll give you this one other example. So here's another example. It's the same thing, really. So if you look at feedback control theory, which is really important to us because like TCP is a feedback controller, right? We don't think about it that way, but generally the way they think about it is you can have high or low gain, or you can have precise or sloppy precision. And so there's kind of a law in there. And you know where it says ideal there, that's not possible according to this law, which is Bode's sensitivity integral. Don't worry about what it says, but I just wanted to show you one that says, hey, you can't do this. And that's like physics, the physics of feedback control, right? And can we make that into engineering? That's what we're trying to do. So the reality is that this trade-off space is really more higher dimension, right? I mean, we were doing this slow, fast, robust, fragile, flexible, inflexible, but there's cheap, expensive, and all kinds of other dimensions. But if we put it in a higher dimensional space, nobody can understand it. And hopefully you don't want that space to be two-dimensional because you have this thing called curse of dimensionality, which is really an interesting thing. It basically means if you have a bunch of data that's high dimension, then it's sparse in any particular dimension and you don't know anything, even though you have a lot of data. So it's unfortunate, but it's part of reality. So really, the space here is much more dimensional, but we're trying to keep it simple so we can understand it and we can, kind of create engineering rules. So All of that interesting. What's the architecture of a complex system then? So what we learned was, through all this biology, systems biology, engineering, the history of how people build buildings, all of these kinds of things, we found that there are kind of these architectural building blocks that are found in systems that scale and are evolvable, and they're in all of these systems. And one is layering, and then the other one is constraints and trade-offs. And there's also protocol-based architecture. We have that, of course. Massively distributed control loops, we have that. And the consequences of all of this are hidden RYF complexity and this hijacking, parasites and predation that I was showing you earlier. So what do we know about it? We kind of know this, right? We know that, so this is like the Internet Hourglass is an example of this, and I'll show you. But basically the core protocols that are involved are usually hidden and constrained, and then above that you have unconstrained diverse applications, Linux kernel or whatever, and then below it you have hardware that's unconstrained as well. And so it's this middle thing, this hidden and constrained core protocol thing, what I'm calling OS here, that's really where the complexity of the system is lying. And this is like the fundamental architecture. And I'll overlay a few things on this. So first off, you can turn that shape in two directions. You can turn it on its side, and that's what the biology guys call a bow tie. And basically what that does is just process information. And then if you leave it in the sort of the hourglass shape, that's a layering of control. And that's exactly what we have in the internet. So I'll show you, hopefully I'll have that. Oh yeah, here's the schematic of the layer, right? So a layer is kind of information processing, and you can see how this works with TCP. I'll show you in a second. But in biology, it's an example is ATP, is adenosine triphosphate. It's like a bunch of materials come in, gets processed into this molecule, and then all of life is built on that molecule. It's where energy gets transferred around inside of all of life. And so basically, the way you kind of look at it is at some layer, L-1, information and or raw materials, because that's what gets networked. Flows are kind of standardized, right? And then they're handed to the next layer up as an abstraction. And that's what provides plug and play. We have that with TCP, things like that for everything above that. And that's what provides robustness, but at the same time causes the fragility because they're standardized interfaces, as I mentioned earlier. So let's see. Oh yeah, anything look familiar, of course, this Internet Hourglass, right? So it really depends on if you look at things as layering, as vertical or horizontal, but these two shapes are in all architectures that scale and evolve. So here's the internet. I just drew it like this. So you can think of, like the TCP layer, what you can think of is that like TCP takes in packets and it formats them and does flow control and all of that, of course, but what comes out of it is our connections, datagrams, and ports. I left datagrams in there because it could be UDP, right? And then that is output to the next layer up, and I just chose HTTP. And HTTP takes as its raw materials, connections, datagrams, and ports. And on the output side, you get like REST, right? So the way to think about it is that flows within layers are formatted into standardized pieces, and then they're handed to the layer above, and they provide another abstraction for the layer above. And by the way, this is the way we build software too, or we try to. I don't know if you can see the bottom of that. Basically, that problem, this is one place where the theory guys did something kind of interesting. What they did was, this problem is called network utility maximization. Basically, it's like saying, can you maximize this subject to the fact that the paths actually all have some capacity? That's really what it is. And they reverse engineered TCP and discovered that TCP was actually trying to solve this problem. And then once that was done, they were able to use different kinds of TCP flow control algorithms and analyze how it worked. So that's a place where you actually got some engineering out of this. Now, the mathematics of that are probably more than we want to do, but nonetheless. And then, okay, here's a picture. In reality, things are more complicated, not surprisingly. This is another one, horizontal transfer. So now how many people have gotten an app from either Play or the iTunes store? I mean, come on, everybody, right? Yeah, so when you get an app, what you do is you transfer it horizontally. You don't rewrite the protocol stack or anything below it, right? It goes across horizontally. So this is, we're calling it horizontal app transfer. And the hardware side does the same thing, but it's kind of modeled on this, which is HGT is horizontal gene transfer. So bacteria can do this amazing thing. They can bump into one another and transfer DNA. You know, it's like you could bump into Michael Jordan and all of a sudden really be able to play basketball or something. You know, that's how it works. And it's sort of like in the app layer, right? So it's the same phenomenon. And if you put all these things together, it's these layered architectures that make robustness and evolvability actually compatible. Without this, you wouldn't be able to have it. So put it all together. So fast, slow, flexible, inflexible, apps, OS, it's the same trade-off. It's all the same kind of idea. So these things all fit together in this way, and I want to show you a couple of examples before I run out of time. So here's the internet architecture, right? So if we put it on the same picture, so the hourglass kind of fits there, and what you have is this kind of kernel of the thing. So it's a TCP layer, right? If I write an application on TCP, you know, maybe all I need to know is about sockets, right? And then I can talk to anybody. I don't know what's going on inside. I have standardized contracts, APIs, but I don't need to know what's going on inside or below. So it's kind of hidden and constrained. It's got to be constrained because you can't change the APIs or the semantics of that, otherwise all the applications no longer work. So it's constrained and hidden like that. How about OpenStack? OpenStack's kind of the same thing, right? Basically, there's standardized contracts in there, but the actual Nova, Cinder, Neutron piece of it is not exposed to the applications or to the actual hardware below it, or software as it is. So OpenStack has the same kind of picture. And the SDN, well, SDN's a little bit more, is a little more squirrely, but it's kind of similar. There's a controller layer that provides a standardized northbound API if people could ever get to there, and standardized southbound. But what's in the middle is not really visible and to the applications themselves and should be constrained. So, because if it's not constrained and it changes, then applications aren't portable and all of that stuff. So it's constrained and hidden in the middle of that. Linux kernel is the same thing, right? I mean, it's the same picture. So, just to do in the 3 minutes I have left, I want to do a little bit of systems biology. So, biological systems, it's the same. You know, it's really amazing that we have a technology that's governed by the same kind of laws. And there's many good examples, and I'll give you a couple of quick ones. This is the bacteria one, right? So horizontal gene transfer, it's kind of like it's slow and cheap, it's very flexible, it's like an app. And then all the way on the other side, metabolism is built into the thing, it can't change. It's like hardware. It's inflexible, but it's fast. This is another interesting one. So there's this thing called VOR, vestibular optical reflex. It's what makes you can move your head and the image doesn't go flying around on the, and so there's a trade-off in here that's the exact same thing. It's basically like this. If you do vision, it's very flexible, but it's slow because it has a feedback controller that looks like this. So you look at something, there's some delay, then you act on it. It's very slow. This vestibular optical, reflex VOR is actually in hardware, so it just acts. You don't go through this thing. And so you have to ask yourself the question about this, is like, could you build a new architecture that beat this, right? Because this is what I want to know, because I want to know if we can build better networks using this kind of, using the learning from this. And so that, down to one minute for this. Okay, so the idea is, can you build a better network? And I talked to a lot of people about this. This is just a network. Can you build a better one? Well, you might be able to, but it's sort of like you kind of sometimes want to wonder what you wish for here, because if you get some kind of cybernetic thing or something like that, or I put a pointer to a URL there where, I don't know if people read this, but Stephen Hawking and some of his colleagues kind of had a call to arms about the same issue, which was, we build a lot of technology, where's it going to go? So, it's kind of an interesting idea about all of this. So, let's see if we can wrap this up. Hopefully I convinced you a little bit. This is kind of a whirlwind tour through a lot of stuff here, but that there are universal architectural features. They're common to biology and technology, and they're the underlying phenomenon that we need to understand in order to go get some engineering kind of rules out of all of this. These are laws, constraints, and trade-offs, And we had all these trade-offs: robust and fragile, efficient, wasteful, slow, fast, flexible, inflexible. And those are everywhere. Architecture and layering, crucial. Hidden RYF complexity and hijacking parasitism and predation is sort of like everywhere, but why is this useful? That's the question. Well, these systems are intrinsically hard to understand. I know that myself. I've had a hard time, even with the network, our network. And RYF behavior it's an inherent property of all of these systems, technology and biology. Understanding general principles, we hope, will inform what we build. Software makes it all a mess. There's no doubt about that. And one of the things that is kind of underlying all of this is that the internet's now it's one of the most complex technological things we've ever built. So the idea is that that we need new and analytic ways of designing, deploying, and operating networks if we want it to scale beyond some point. Now, what is that point? I don't know. Nonetheless, many of our goals for the internet architecture revolve around how to achieve robustness in the most general way, like I was describing. And that really does require a deep understanding of this interplay between complexity and robustness, modularity, feedback, and fragility. These are kind of the main building blocks of all of this. Yeah, and by the way, all of that stuff's not superficial, it's built in. And then this architecture that we have arises from designs that cope with uncertainty in their environment and their components. And the same designs can make protocols hard to evolve. By the way, why was it hard to deploy IPv6 or IPsec? Because they lived in the waste part of that thing, and they were supposed to be hidden and, not changeable. That was what was hopeful. So, to kind of close this up, it seems obvious that understanding these features and trade-offs will help us achieve scalability and evolvability and all the properties we want from the network going forward. It will definitely help us. Whether or not it's necessary or where it becomes necessary, that's another question. Maybe that's what's not so obvious is that this requires kind of a mathematical theory of what network architecture is. If we want to be able to analyze and compare and simulate and optimize things like that, we need some kind of formalism, models or something. And mathematics is the natural language for this, so it makes it all hard for many of us. As engineers, we also like to solve problems. This is building tools to solve problems. And by the way, my friend John Doyle always says that engineers always know first because they always have to solve problems, and the theory guys come along later and then explain why they solved this problem so beautifully. So that's one of the reasons that, why we need to talk to these guys, building bridges. This is a first cut. I just wanted to give you a picture of this. Basically, again, this is this constrained optimization problem, and then you just take it apart, you make layers out of it. The machinery to do this is pretty daunting, but the idea is pretty basic. As I mentioned, TCP was reverse engineered this way, and actually various versions of TCP were built with different properties this way. But also the stable path problem, which is just the BGP problem. Tim Griffin did this, showed that BGP was solving this kind of problem. So we need something more than what we have is the bottom line here. And, finally, to going to some of the, I'm over, okay. What happens to the speaker when they go over, like they fall through the floor or something? Finally, in the bridge building thing, my colleague John Doyle and I are doing this thing at SIGCOM, so if you happen to be at SIGCOM in the summer, come see that. I think that's all I have. Can I take a question?
We're running a little long, but we got time for a couple questions. Bill Norton was up first.
Hey, a quick question. Your last point kind of made me start thinking about that constrained part of the hourglass, and you mentioned IPv6 in there, and it kind of made me wonder, are there any other biological imperatives that we can look at where we showed that we can in fact transfer that constrained part that works pretty well into a new constrained part? Do you see any of that in biology?
You do. Actually, the systems biology thing is so interesting because not all of them, but many of the engineering things we see and many of the things we build into protocols are actually there. So I'll give one quick example. So in the transcription network of E. coli, there's something called a type 1 coherent feed forward loop. It's just a control structure. And basically what it is it's a hold down timer, just like you have on your interface on ISIS, right? It's a hold down. And it does exactly the same thing. The bacteria doesn't want to start making proteins that are going to chop up sugar if they're not really there. Just like you don't want to flap an interface if it's going to come back within a certain amount of time. It's exactly the same circuit. So yeah, there's a lot of that stuff.
I think we're over here next.
Oh, Jay Kuhn, Semantic. So given that we've seen the last 20 years of networking, if you were to take some of that robustness, fragility graphs, and you were to add a time axis to it, what would that plot of that field curvature look like, do you think? Do you think that would angle up and to right or angle downwards?
Yeah, I understand what you're saying. I think the shape of the curve will maintain that kind of thing because it's inherent in the trade-off itself. Where it sits, so you have these two axes like this, right? And you have that curve that look like this. You can move that in and out, right? But its shape stays the same, right? So the closer you get into the optimal, which is closer to the kind of axes, the better you're doing. But a lot of times the stuff we build is way out because we don't know how to do it any better. So.
All right, now we'll do the three folks at the microphone, starting in the back over there.
David Barak, AT&T. When you described adding the second router, when you're making decisions like that, how would and you're trying to determine whether that would make the system more robust or more fragile, how would that not be the equivalent of solving the halting problem?
Yeah. Is that decidable, in other words?
Right.
I don't know the answer to that. We don't have machinery that will tell us that. There might be heuristics that we can use. I don't know. That's kind of part of the call to arms here that I'm trying to make to you folks is that it'd be nice to have machinery that would tell us whether or not that problem or a problem like that was decidable. We don't.
Over here.
Dave, Clark Gaylord, Virginia Tech. Great talk. I see
Thanks.
you've got a paradox in the layering principle relative to complexity. Throughout, you gave the layering principle, or layering in general, as an example of complexity that happens in systems. At the same time, you sort of conclude with layering constrains the amount of complexity you can have in the system because it prevents components of the system from interacting across layers too much. Is that a paradox in how we see layering as an element of complexity, or does it prevent complexity?
That's a good question. I mean, really what layering is part of what complexity is. It's not a separate thing. So remember I said complexity is really about structure. Not, we think about it, you got a lot of different things, but it's really about these structures, and this is one of the key ones. So, and it depends on where the layering that you're looking at is. So if it's in the core piece of it, remember I was saying there's like an OS. That's just a metaphor, but like an OS. In that case, that needs to stay pretty hidden and pretty standardized in terms of the contracts it has with things above and below. But the other layers can change, right? And that's the idea, because that's what we see in the IP network today. So, Sean
Dialing, Treasury Department.
Seriously?
Yes. So for customers, investors, and regulators, how can we look at complexity, and since we're not allowed to go through that hidden part, can we figure out whether or not we're in the bad part of the curve or the good part of the curve or about to fall off the cliff?
So that is the kind of question that you want to be able to answer, right? You have two
I would love to answer that question.
Yeah, and that's part of the call to arms here. We don't have the machinery to answer that. Let me give you a simpler example of that. I have two network designs. Which one is where on these curves, right? We don't know that. We don't have the machinery to do that.
Until we go over the cliff, and then we know we got too close.
Yeah, engineering heuristics, right? We learn.
All right, thanks a lot, Dave.
Thank you.